Okay, so this tutorial will cover solid phase peptide synthesis. If you've already watched the video on solid phase DNA synthesis, then this is going to um, sound rather familiar. It's a similar kind of approach. We're using a solid bead as a platform to build, in this case, a peptide, right, an amino acid sequence. So we're making amide bonds. We're not making phosphodiesters like we did in nucleotides, but we're taking advantage of the same kinds of concepts here, where we want to have a single nucleophile, a single electrophile available to react at any time, so that we can get very high yields. Remember, if you're going to do many of these coupling reactions, you have to have very high yields. Otherwise, you need to start with a dump truck load of starting material at the very beginning to get a thimble full of product at the very end, right? So again, if you do two couplings and they're 90% yield each, then the overall yield is going to be 81%. If you do those same couplings at the same yield and you do 10 of them, then your yield goes down to about 35%. So you're just taking the percent yield in its decimal form, right? So 0.9 raised to the power of the number of couplings. So this is a kind of the limiting factor here in how many of these couplings you can do. Even at very high yield, you get very diminishing returns with increasing numbers of couplings. So we want to be able to tether our synthesis down to the surface of a bead, so we can add lots of reagents, starting reagents, so that we can maximize our yield, so that we can get a useful amount out at the end. And like we talked about in the DNA synthesis, we're going to build this backwards to what you would expect. Nature is going to build amino acid polymers, so peptides, from the amino terminus towards the carboxy terminus. So we're going to be utilizing that kind of directional flow. Here we're going to be going backwards as well. We're going from the carboxy terminus to the amino terminus. Okay, we're taking advantage of the reactivity that we have. So the first step is going to be to immobilize our residue, our N residue, which is going to be our carboxy terminal residue, to the bead, and we're going to make an ester linkage. Okay, and like we talked about for the DNA synthesis, we need to protect reactive side chain functional groups in our amino acids, so things like hydroxyls, thiols, carboxylic acids, and amino groups. Okay, remember, if we deprotonate a hydroxyl or a thiol, they become stronger nucleophiles. If we deprotect a carboxylic acid, it also becomes a stronger nucleophile. And amines are pretty stout nucleophiles to begin with. We also then want to be able to protect the amino terminus of the protein, because we don't want that to be reacting. We're going to protect it. Again, we have two different ways. We can do it as this Bach protecting group, or FMOC. Now in the book they talk about Bach. Here I'm going to show you the FMOC. So again, you can compare and contrast those two. So this is the FMOC reactant. Here's our amino acid. In this case, we just have alanine. We're going to react the amino terminus here to get our FMOC protected amino acid. At this point, then, we can use the fact that if we deprotonate the carboxylic acid, we get a carboxylate that can react with this benzyl halide to give us our ether-linked amino acid to the bead. Remember, this is our carboxy terminal residue, right? So we've got amino terminus, amino group, alpha carbon, side chain, carboxylic acid. So this is the free end. We're going to be building off this direction. So again, like we talked about in the DNA solid phase, the next step is going to be to deprotect that reactive group that we want to act as a nucleophile. So here we're going to deprotect the amino group. Okay, remember, the carboxylic acid's tied up in the ester bond of the bead, and we're going to use chemistry that just deprotects the amino group and doesn't touch that that ester linkage. Okay, and we're going to bring in our N-1 residue, which is one residue closer to the amino terminus. We're building in that direction, right? We've already got our carboxy terminus, and we must have appropriate side chain protection. So anything with a hydroxyl, a carboxylic acid, a thiol, etc. And we're going to activate this carboxylic acid in the presence of our bound carboxy terminus. In this example, we're building a 10-mer here, so that's why it says residue 10 on the bead. And then we're going to generate an amide bond between those two peptides. And then we just keep repeating step 2 here until we've reached the amino terminus. So we're just going to add in the next residue that we want, deprotect. What we're going to bring in is a protected amino group. And then we're going to activate the carboxylic acid. We're going to use that to build. Okay? So we'll show you the steps here. So here's our incoming residue. This is our residue 9. Okay, remember our residue 10 is bound to the bead. We want to make a 10-mer. Now we're bringing in this amino acid, which is a serine. Here's our side chain, CH2O, and then that benzyl group. So this is a protected serine. Its amino terminus is protected as an FMOC here as well. And this is the coupling reagent that we're going to use, which is called a carbodiimide. And depending on what these R groups are, if these are both cyclohexyl groups, it's just a compound called dicyclohexyl carbodiimide, or DCC, a lot of time. So we're using the carboxylic acid of our residue as a nucleophile. Okay? Because remember, there's no pH at which we can put together 2 amino acids and have amide bond formation, because we're going to have either one electrophile and no nucleophile, or 2 nucleophiles, depending on the pH. So if this carboxylic acid attacks this electron deficient carbon, and we pick up a proton here from our dimethylaminopyridine, which is a catalyst for this reaction, then we get this activated form of the carboxylic acid. Okay. Now what we've done is we've removed the pH dependence on the character of this carboxylic acid, and we've given it a good leaving group. So now our carboxy terminal residue, the amino group, can act as a nucleophile. We can attack here, and we get loss of our carbodiimide functional group. It's going to give us this product, and we get our amide bond formed. Okay, and then the next step is going to be to deprotect this and go through the next coupling step. So in this step 3, we're going to deprotect the new amino terminus that we've made, and add any of our next residues. We're going to keep going through that, and then we're going to at the very end, we're going to deprotect the amino terminus, all the side chains, and cleave from the bead all in one reaction. And we'll show you how to do that. And usually the next step is to purify this final product using something like HPLC, which is going to get a nice clean single product at the end. So when we have our peptide, and again I've just shown this dipeptide here, so here's our alanine, which is our C-terminal residue, and our serine, which is in this case our amino terminal residue. If we add hydrofluoric acid, then we can deprotect the FMOC, we can deprotect the side chain protecting groups, and we can cleave off the bead all at the same time. Okay. Now acid is going to cleave all of these, so what I want you to do is think about how you're going to cleave the FMOC off this selectively when you want to be able to deprotect and add the next residue on here. Okay, so it's important to think about if we wanted to make alanine, serine, and maybe another alanine here, right? If we got this product, we don't want to go through this complete deprotection yet. We want to add the next one on. We have to be able to take this off selectively, keep all the protecting groups on the side chains at that point, and keep it linked down to the bead so that we now can use this as a reactive group to grow the chain. So when you think about how to do that, okay, you have enough chemical knowledge to be able to figure this out. Okay, so these are the tools for peptide solid phase synthesis.